Welcome to Optimization with Stella. My name is Kareem Shashakli, and I'm very pleased to introduce Bob Eberlein, who will give this presentation. Bob has decades of experience in system dynamics. He's been involved with the society forever, and before coming here to become co-president at IC Systems with me, he was the driving force behind Vensim. He has delivered many optimization workshops and classes, and I think you'll really enjoy this. Before we start, I want to go over a few details about how to use the GoToMeeting setup, the GoToWebinar setup. At the top, you'll see there's a grab tab that lets you slide, hide, or display what GoToWebinar uses to help you see what's going on. You can enter questions at the very bottom, and in the middle, if you're not hearing audio or it's coming or going, you can press sound check, which is at the top of that. So make sure everything is working on your audio, and remember, you can submit questions. Please submit questions at the very bottom. Here's Bob.
Great. Thank you, Kareem. And thank you all for attending. So what we're going to do today is introduce sort of optimization in Stella, and we're going from 0 to 60 pretty quickly. So I'm going to start really with the very basics of how you just do the mechanics of an optimization, and then give several examples showing some of the different, more sophisticated features related to optimization. So we're going to introduce the basic concept, what it is, for some of you who may not even know what that is, and then the mechanics, an example, and then combining optimization and sensitivity, which is a very powerful way to learn about systems, and then optimizing trajectories, changes over time. Look at situations where you might have multiple optima and how you can deal with that, and then some summary observations and extensions. And of course, we're going to have a Q&A session where you can ask questions and hopefully get suitable answers. So the concept of optimization is, in a sense, an extension of the concept of a simulation. So a simulation takes structure, you see that on the left here, and it turns it into behavior and shows how things change over time. So an optimization shows us how to achieve the best result. Now, that's kind of an interesting statement because the best result isn't as obvious when you're dealing with simulation models. And one of the first things we need to do in optimization is define better, what it is a better result would mean. And then we need to determine what parts of a model to change. Typically, those are parameters. And then we change those things until we get to what is a best solution. So let me start with a really simple example, which is a polynomial, y equals ax squared plus bx plus c. And these are this is kind of the shape of that polynomial. You can see over on the right. And the optimization problem is what value of x makes y as big as it can be. So you'll notice in this that the tails go off downward to minus infinity eventually. And that means that there's an internal solution. And if you remember your calculus, you can take the first derivative of the expression, which is 2ax plus b equals 0. And we can use that to solve for x, which in this case would be 4.25. So what I want to do actually is show that simple example using Stella. And so we'll switch to Stella. And I will open up a version of that model that has the same kinds of inputs and computes y. And if we were to just run this model and go along and change x, as we get it bigger, we can see that the value of y is going up. And it will continue to go up while we get it bigger. And eventually, if we get it big enough, you'll see the value of y now goes down again. So in a sense, optimization is the process, it's a little bit more sophisticated than this, but it's the process of hunting around and finding a value of x to make the value of y as big as possible. So the basic mechanics of doing an optimization are first to define the payoff. In this case, we're just going to use y as the payoff. I'm going to go through and show you how to do that. And we can use the value of y at different points in the simulation. It doesn't really matter for this particular example. And then we have to specify what to search over, which will be x, and then we get to see the results of our search. So let me do that. So I need to open up the panel for this, and on the panel on the bottom, you'll see a magnifying glass with a graph through it, which is a model analysis tools. And what that does is it lets us define sensitivity, payoff, and optimization. And we're not going to do any sensitivity for this model, but we will come back and show a model where we do use sensitivity. Payoff, as I said, is just y. So I click on the payoff. It's got a default name of payoff, which is quite appropriate. And I select which variable I want to use. I'll be y. And we give it a weight. There's only one variable. The value of the weight isn't that important, but the sign is. So we'd give it a -1 if we wanted to minimize, and a 1 if we want to maximize, which is what we want to do here. And you can use the final value at the end of the simulation, the value over the entire run, which is actually basically an accumulation of that value, a specific time or a time period, accumulation over a time period. In this case, all would give the same results, and we will just use the final value. That defines the payoff, and then to define the optimization, we have to go in and tell it. The default settings in this are going to work for many cases, and basically we need to select a parameter, which will be x. We need to tell it what value range we want x to go through, and we will use -10 to 10 as the value range. I'm going to leave other things alone. And I need to tell it what payoff we want to use, and that will be the payoff called payoff. And this optimization is named optimization. You can define multiple payoffs and multiple optimizations if you want to switch between them. For the simplicity of demonstration, we're going to be sticking with just one definition of optimization as we go through the examples today. Once I've defined all that, if I click on the little checkbox here, you'll see that there's an O run in the bottom left-hand corner. There's also a run button on the panel itself. And both of these do the same thing. I am used to clicking on the O run, so I will click on that. And it will go through and it will start an optimization. It will make 34 runs. It found the best value of 34 was 34.125 with x equals 4.25, again, matching our analytic solution. And then it runs a final simulation and shows that value. And here you can see the value of y. And any change away from 4.25, this isn't a comparative graph, so I guess you can't see that, will decrease the payoff relative to that. So that's the basic mechanics. It's really very, very simple to do. A lot more of the complexity is really in understanding what it is you're trying to optimize over and defining the payoff. So let's go to a slightly more interesting example. So we're going to try and optimize a supply chain model. And this is a model. Let me open it up in Stella. That basically has orders coming in. There's inventory. It's the same as the one we show at the beginning. If you run this model, it shows that same behavior where there is a increase in orders, and as a consequence, inventory goes down, goes up, and then moves around like that. What we want to do in this particular model is define our payoff. And for this model, there's a rental rate on inventory, which means there are holding costs. And if you get a backlog, you can lose customers who are dissatisfied, and so you don't get them for shipments. And so our net income is just the amount we ship times the margin we get per each item shipped minus the holding costs. And that gives us cumulative income, and really it's cumulative income at the end of the simulation that we want to try to maximize. So I go into this particular model. Again, this is now set up with the payoff defined as cumulative income at the final value, and optimization specified over what we can optimize over. And what we can optimize over are the three parameters over here. Inventory coverage, how much inventory we hold relative to orders that we expect, the time to correct inventory, and the time to average orders. So we're going to have inventory coverage running from 1 to 100 days, time to correct inventory from 1 to 100 days, and time to average orders from 1 to 100 days. Then we run the optimization and see what happens. So I'm going to click on O-Run down here. And what we'll see is that it makes 77 runs. It picks an inventory coverage of about 52 days, time to average orders of very close to the maximum, and a time to correct inventory of about 51 days, which is kind of a pretty large number. And one of the things that you will notice is that the inventory kind of goes down, just glances off zero for a little while, and then goes back up. So there are a small number of lost orders. You can see that here. I can open that up a little bit. A small number of lost orders that are appearing really only over the course of a day. And cumulative income is what it is. And the red line, which is run 2, now shows the value versus our original run. And we can see that there is a substantial improvement. So that's optimizing that. But what we've done is we've optimized against a specific order stream. And the question is, what happens if there are different order streams? And that gets to combining optimization and sensitivity. So before I get into that in detail, let me show what would happen if, for example, I'll restore this so we get rid of the runs. There is a parameter in here that lets us change the type of order from a step to a randomized order. And now I can optimize it with a randomized order. And here we can get the comparison. Payoffs are different because it's actually going to be a different mean value here. But we get an inventory coverage of 24 days versus 51. The time to average orders is 58 versus 99, somewhat shorter, but still fairly long. And the time to correct inventory is 27 versus 51. So it's somewhat more aggressive in correction of inventory. And if you look at the behavior of inventory, you can see that it goes down and it does spend some time very close to zero. And if we look at this again, the lost orders, we get basically only one day with a significant loss in orders, another day where there's a very trivial loss in orders. And this is happening because inventory is just touching zero. We have just enough to ship and we're allowed to empty it out. Now, a different model might have a different formulation for whether or not you can ship from inventory, but in this model, you can ship as long as you have any inventory at all. So what we want to do is say, well, we get one result when we run it with one set of demand, with one demand pattern, and a different result when we run it with a different demand pattern. So what we're doing effectively is optimizing to specific assumptions about demand. And that is not a robust strategy for optimization because certainly there are other order streams than a step input. We've used the randomized one, and certainly even for a randomized input, there are other sequences of random numbers that might be generated. So a way to get around that lack of robustness is to do sensitivity over the assumptions in the model. And this would be essentially the type and extent of order variation as the thing that we're going to use as sensitivity. And an important note, although it may seem obvious, is we can't do sensitivity in a parameter that we're going to then be optimizing over. That would give us kind of nonsense results. When we do sensitivity in this way, the payoff, instead of being the result of a single run, is averaged across the various sensitivity runs. It's also a choice to pick the worst payoff, to try and find an optimum that makes the worst thing as good as possible. It doesn't really make sense for this example because these demand streams will change the net amount of the average number of orders, which in turn would change the payoff. So you wouldn't actually be optimizing over something that makes sense. And then when we do this optimization combined with that, so if I just run sensitivity, let me just restore devices and run sensitivity so we can kind of see what happens there. We can see that there is a fair bit of variation, and this includes different random noise sequences and different types of demand. One is a noisy demand, and one is a change in demand. And that's what orders and inventory would do. When I click on O-run, what it does is it optimizes. Sorry, I haven't changed the changes to use sensitivity yet. It did the same thing we did last time. And I'll go into the optimization setup and say that I want to optimize across sensitivity simulations. So I select sensitivity there, which is the name of the sensitivity simulation. And that sensitivity simulation is varying. The switch determines whether or not we use a random distribution. The size of the step, the increase in demand, or it could be a decrease actually. This varies from -5 to 10. A randomized standard deviation, how big the variation is when we're using the randomized thing, and a noise seed, which determines the actual sequence which will be drawn. And one thing I want to point out in the sensitivity settings is there is a noise seed that I've entered for sensitivity. So if you don't enter a noise seed for sensitivity, you'll get different sensitivity results each time you run it. If you're combining sensitivity with optimization, that would be a problem because the optimization assumes that the same set of parameters will always yield the same set of results. So it's really important that you include a noise seed when you're combining sensitivity and optimization. So the optimization is now going to use that sensitivity. And when I click on O-run now, instead of running just once, it's going to go through and run the sensitivity and then optimize over the sensitivity. Takes a little bit longer. You can see the kind of progression that's going on in the bottom toolbar here. And in the end result, we get payoff of 1520, which is a little hard to interpret because it's the average across the sensitivities. But the inventory coverage is 10, which is a bit smaller than it has been. The time to average orders is still quite large, 94. And the time to correct inventory is 11, which is kind of similar to what it was in the noisy case. And you'll notice relative to the original run that the amount of variation in the inventory is quite a bit smaller. So it's picked a set of parameters that keeps inventory in a narrower range than it was in the original simulation. And we can see inventory and orders. And if we want to go in and do just a run, this is actually the initial run where there's a doubling of the number of orders. And we can see in that particular case, it takes the inventory down to 0 and it holds it there for quite a while. So it actually performs pretty badly for that particular example. But when weighted against all of the other examples, we get an optimization that performs relatively well. And so that is always true when you're doing optimizations over sensitivities. There are going to be some sensitivity runs where performance is less than you might expect, and others where it will be good. The results are a little less extreme when we do this, and we can compare that to the original optimization. Now, those of you who know this type of model will point out the obvious, that this model does not have a supply line correction in it, and a supply line correction is one of the most effective ways to improve performance in a supply chain model. And in fact, if we were to do that, we would probably get better results than we would get doing this optimization. And that's kind of a warning that optimization is a wonderful, wonderful tool, but you don't always see all of the kinds of structural changes you might make when you're doing an optimization. And it's important to think of those in the context of the optimization as well. So what happens if we want to optimize a trajectory rather than a single point value? And that I've sort of shown a trajectory of you might want to invest different amounts at different points in time. And since optimization is done over parameters, how can we do that? And so the model I'm going to show you has a technique of doing that. And it's basically a technique of switching parameters that are used during the simulation itself so that you can set up a trajectory. And so the amount of investment is switched between different values at different times with the equation that it's the sum of variable investment by time multiplied by is this time period, where is this time period is this somewhat funny variable that says if an integer of time is the current time period, -1 because this is a zero-based model, then it has a value of 1, otherwise it has 0. And what that does is it switches between the, in this case, 20 elements of is this time period and gives a 1 to the first element, and then the second element from time 1 to 2, the third element from 2 to 3, and so on. And when we do that, we can set up an investment trajectory by optimizing the model. And so to do that, I will close out of this model. And I will open up multi-period. And this is a oil field depletion model where you've got some amount of reserves that are in the oil field. I can just run this, see the behavior a little bit. You invest. When you invest, you build capital. Capital lets you produce the oil, bring it out. That generates revenue, generates a net cash flow. This particular model has a scrappage, so you can throw away your capital at the end, recover some amount of the money with the fractional scrap value as a payment, and which goes again into net cash flow. And all of this comes together and gives us a net present value of cash flow. The default settings of this model have a discount rate of 0, which means the net present value of cash flow is the same thing as the accumulated cash flow over the course of the simulation. So if I now take a look at the optimization setup for this particular model, what we'll see is that we have investment by time with a star in it. And that is shorthand for saying every element of investment by time. So if we were to pick investment by time, we have a choice of its 20 different elements, and we have a choice of using star. So the star is a shorthand way of saying get all 20 elements. And what we're saying is for any element, let it vary between 0 and 100,000. And now what we're going to do is optimize this to try and find a trajectory that maximizes our net present value of cash flow over the course of the simulation. And again, now it's going to take a little bit longer. It's going to do, I think, about 1,500 simulations. It's going to find a set of values which correspond to this investment profile shown here. And I'm actually going to get rid of the first run, so we only have that investment profile showing. Just be a little easier to see when we do the next run. So that shows us an investment profile. And optimization certainly gives you an answer, but the interesting thing about optimization is also often asking, well, what happens if I change something in underlying model assumptions to the optimization result? We did that with the supply chain model to look at different order streams, but we might do that to say, well, what if I have a different assumption about how I view the future, which is to say I want to have a discount rate, let's say 5%. I can now re-optimize this model with a 5% discount rate. And that optimization comes up, and you can see now it's the dashed pink line. There's much more investment right in the first period. It does jump down to 0, and then it goes back up and holds a little bit more steady. And one of the things I did not point out, but it's worth looking at in terms of the capital, is that in the first optimization with a 0 discount rate, you'll see the capital is more or less constant. It's bumpy because we've got this investment is itself kind of bumpy, but it's more or less flat. Sort of jumps it up to a big value, keeps it flat for a long time. And then you can see what happens, this declining exponential decay, is when we've stopped investment altogether and we're just letting the machinery kind of fade into the background before we scrap it. And it's decaying in value. And in the green case, we go up a little faster, and then we let it drift down a little bit. But then we actually stop the investment one year earlier, and again let it fade over time. So you can use the optimization combined with behavioral assumptions to think about the implications of those behavioral assumptions on what the best values are and what that might mean. In this case, it's the discount rate, which not surprisingly pushes things forward, so you do things earlier in time. Higher discount rate pushes investment earlier. Now, one of the things that will often happen when you're dealing with optimization is you may end up with models that have multiple optimum, more than one place where you have an optimum value. And that's a bit of a challenge in doing optimization. And I'm going to show you how that manifests, several different solutions to it, and kind of an explanation of why it happens for this particular problem. So the model that we're using for that is a fisheries model. And it is a fish stock, which you can catch, or a fish can be born and they can die. And if you catch them, then you get a cumulative catch. And if I just run this model, I can see that the fish stock does that, my cumulative catch does this. And if I change the number of days fishing, if I make it lower, the cumulative catch goes down, no big surprise. But the interesting thing about this model is as you increase the number of days fishing, eventually, you catch so many fish that you actually make the population of fish extinct. Now, that's kind of interesting, and we can optimize this model, the number of days fishing with an O-run, and it will tell me that I should try and fish for 31.5 days, and when I do that, I will get a fish stock that looks like this. And the interesting thing is if I fish for slightly more than that, boom, immediately we get an extinct population of fish. And what the optimization has done is it said, what's the biggest number of days fishing I can have before I make the population extinct? And you can see the consequence of that is the fish stock is going up only very, very slowly at first, almost flat. And the optimization has kind of pushed us right to the edge of a terrible abyss in some respects, but a point where the number of fish being caught would eventually go to zero as you made the population extinct. Now, in a fishery where you don't really know what the fish stock is, this is actually a real problem. And one of the things that we can do to help understand this a little bit better is, again, you combine sensitivity with optimization. So sensitivity here is going to be changes in the initial fish stock, and we're just going to let it vary between 250 and 2,000. And if I run a sensitivity run on just the last day's fishing I had, what you can see is that the different fish stocks kind of bifurcate into two sets of populations. Three of them, which happen to be run 2 and 3 because this is incremental increasing, the fish stocks go to zero because the fish is driven out to extinction. And the other ones, they all go to a steady state, which is the same value. Some of them came from above and went down. Some of them came from below and went up. So if I optimize this model, so let me restore the devices. Let's optimize over those sensitivity runs. To do that, we do the same thing we did before. We go to the optimization. And the optimization, instead of having no sensitivity, we will do using the sensitivity called sensitivity. And again, we're going to use the average. Think about the worst in this case. That would be the smallest population. And optimizing that would be the same as optimizing it with an assumption of the smallest population. When we do a O-run here, it comes back and it says after 12 runs, we get 20.1 as the day's fishing. And at 20.1, everybody survives, which is pretty cool. But what happens if we start the day's fishing at, say, a number of 32 or so, which is slightly larger, and do an optimization of that? Well, then we get an optimization that says we should be fishing for 37 days. And when we fish for 37 days, we have 2 populations going extinct and then the rest of the populations existing. And we're getting a payoff now of optimization. Okay, payoff is 297. And what happens if we make this even slightly bigger, say 62? And do an O-run, and it comes back to 37 again. And, well, okay. I know there are more than one. Are there more than 2? Well, that's something worth understanding. And there are a couple of different ways to understand that. So here we have a model that has more than one optima. How do we figure out what the optimum optima, or the biggest optimum, is going to be? There are 3 different approaches I want to outline for that. 2 of them are pretty general. One of them is kind of specific to a simple model like this, but they're all worth looking at. So the first one is something that is basically to say, okay, I've got the optimization I did, but why don't I just start again 10 times? And I'll start again by randomly choosing the number of days fishing on the interval I've specified. So I said it should be between 0 and 100. I'll randomly choose between 0 and 100 and then optimize from there. And when I do that, when I click on O-run here, it keeps going again and again, and it gives me a bunch of different runs and a bunch of different results. So restarting the optimization from 25, and I get 28. Restarting the optimization from 74, and I get 43. Restarting the optimization from 46, and I get 47. So 43 gives a payoff of 303. 47 gives 281, 259. At the very end of all of this, it says, okay, the best I found was 303 at 43 days. So by randomizing the starting point for the optimization, we can find then it will converge to different global optimum, and we can see which of those optimum is valuable, is the best. And in addition to that, we get some feel for how the starting point relates to the ending point of any given optimization, which is valuable. So that gives us kind of more information about what's going on. That's one approach to doing multiple optimization. Another approach, if we think about it for this simple model, would be to just thoroughly go through all the different possible values we could have for the number of days fishing. And so I could do that instead of using a Powell search. I could use what's called a grid search. And I could run the grid search from 0 to 100 days fishing, and say I want to run 99 steps. You're only allowed to run 100 steps in a 99 or fewer steps in a grid search, because in more than one dimension, grid searches become very, very complicated very quickly. And there are a number of different types of grid search, but the exhaustive one will basically just run through the sequence. And if I do that and I run an O-run, it's just going to run through all of the different values, and it's going to find the number of days fishing at, it's not 43 because it's only doing increments of 1, but basically it finds it at the same place. So that is a grid search, which with 1 or 2 parameters can be fairly effective, but because of the number of possible combinations is basically equal to the number of parameter raised to the power of the number of steps, this becomes a very, very large number very, very quickly, and can overwhelm a computer. I mean, you just don't get to explore as much of the possible solution space as you might want to. So another approach to do this is a different optimization technique or algorithm altogether. It's a different method, we call it. And that method is called differential evolution. And this is a method that basically creates populations of by randomly selecting the parameters to start. So there'll be 20 populations, or a population of 20, I guess is a better way of putting it. And then we'll go for each generation, and it uses a genetic algorithm to combine the characteristics of the population in order to come up with a overall solution. And again, we're going to maximize that. When you're using this, there's an option to maximize or minimize. And if we run that as an O-run, we can see that it runs through the different generations down in the bottom here. And then we can see that it also arrives at 42.99 with a payoff of 300.9. So it's slightly different than the Powell, and it's slightly less accurate, but more robust, I think that's probably the best way to characterize this, because it really has a wide breadth of variety. It gets within the different population groups. And as a consequence, you get, if there are other local optima, it's much more likely to uncover it. As with the grid search, it can be quite time-consuming, although relative to a grid search, it's actually pretty efficient. So the key thing here is that the Powell method, it starts at a point, and then it kind of moves from that point. And it doesn't always move to the optimum that is closest to the point you start at, because what it does is it starts with a slope, figures out where it tries to jump to a point, and it might actually jump past to the point that is the local optimum, but it will go to an optimum point. It actually guaranteed, actually that's not quite true. So it matters where you start is the bottom of it. So the randomized starts lets you just start in a bunch of different places. That's what the randomized start does. Grid search just deterministically starts at different places. And then differential evolution basically randomizes the starting points, but then it combines the populations and their starting points at different sets of values. Now, this example is interesting because it's worth just taking a look at what's happening. And the model I'm going to show you is interesting in its own right, because what this model does is combine basically the sensitivity, or represent the sensitivity as an array. So fish stock, rather than being a single fish stock, is arrayed over. Actually, let's go look at the initial fish stock, and we can see what that looks like. It's arrayed over a dimension where there are different values for the dimension, and we tell it that it's 250 times dimension 1. And what that means, if I just hover over initial fish stock here, we've got 250, 500, 750. So those are the values, same as the set of values that I had used in the sensitivity simulation for the non-arrayed version of this model. And what we can do is in a single run then, we can get the average amount of catching by looking across all the different runs. And then I can see what happens to catching as the day's fishing goes up. And you can see that if it goes to 0, it's obviously at 0, then it grows for a while, and then it plummets and goes towards 0. And if I run a sensitivity on this particular model over the number of days fishing, so this is really just a plain sensitivity simulation, I'm going to let the number of days fishing vary between 0 and 50. I'm going to do an S run. And what I get is I get a payoff, which is really average catching. And you can see what it does is it increases roughly linearly until you get to the point where you make a population extinct. Then it drops down because one fewer population to draw from. And again, it starts increasing roughly linearly as we're drawing more, drops down roughly linearly, drops down more because the populations now there are fewer of them left. So when we take one away, it's a bigger impact, drops down more, drops down, and then drops down to 0. And we basically have made them all extinct. So in this particular model, we're actually doing the steady state catch, not the cumulative catch. So it's the amount of catching at the end of the simulation that's being optimized over. Okay, so that was really fast. I've gone through that. These models are going to be made available to you so you can kind of work through them at your leisure when looking at the recording. But let me get some summary comments. So optimization lets you find values that maximize a payoff. Payoff definition is important, and I didn't really spend any time in here, but in many cases, defining a payoff is really, really hard to do, and that takes some work. The larger the number of search parameters, the easier it is to get stuck someplace in doing optimization in general. Most of the optimizations here were a relatively small number. The trajectory one was 20 different values, and it's easy to get kind of hung up and have things not converge. Convergence does depend on setting good control values. The defaults usually work pretty well for all of the different methods that are included in Stella, but that's not always the case, and experimentation is really the way to kind of figure out what will work best. Robust results may require some amount of sensitivity. Just because you've optimized something doesn't mean you really have the answer. Multiple optima may require multiple starts, differential evolution, some other mechanism for seeing whether or not something's going on. And doing that is a good idea in any case. I didn't talk much about differential evolution, but it's actually a more broad optimization technique than what I've shown here. You can have multiple criteria that are potentially conflicting, and that allows you to create trade-off surfaces that shows how much of one thing you can get versus how much of another and how they influence one another. And then finally, just calibration, the process of fitting a model to data, is something that uses optimization as a computational engine, and we will be talking about that in a future webinar. So questions, welcome any questions that you might have. This is a list of some of the upcoming webinar topics that we'll be doing using Stella to trace causality, creating and analyzing sensitivity simulations, and then calibration and data handling. So, okay, I hope that one of the first questions is whether or not a global or a local optimum. So that was part of the testing, and typically there's a number of additional starts you can do, and just having one additional start in is often enough to tell you whether or not there's something different. So if you're using the Powell optimization technique, using additional starts, at least one, is a pretty good idea. So these optimizations are all constrained in the sense of you specify the minimum and the maximum values for the parameters that you are optimizing over. If you want to do something that is more nonlinearly constrained or something, what you can do is create model equations that get parameterized by values that can then come back to a minimum or maximum. That is not always a trivial thing to do, but it's usually something that's practical to do. So beginner books on optimization So there are lots of books on optimization, but most of them speak to the techniques for doing optimization, not really making use of optimization. And I'll have to get back by email to see whether or not we can find out with any good references of written material on kind of introduction to optimization and using it with practical models, because I don't actually know of anything offhand. So in terms of the distribution of the question is whether or not there is a way of looking at what is the distribution, what types of distributions are generating the observed data. Stella is not particularly good at figuring out distributions. You can, if you're kind of familiar with maximum likelihood and are willing to do likelihood surfaces for different distributions, use Stella optimization as a technique for finding that, but there are better tools out there for just discovering the distribution of underlying data. The optimization, the random number generators in Stella there's a broad variety of them. So in terms of the sensitivity and in terms of selecting parameters, selecting time-varying changes, there is a very broad set of random number generators that you can choose from. So can Stella maximize against multiple criteria? So that is what the differential evolution method does. I didn't have time to go into it here, but it really maximizes each of the different criteria and lets you show a trade-off surface. The other thing you can do with multiple criteria is combine them into a payoff, and that's a matter of weighting the different criteria to decide which one is more important and which one is less important. And the ultimate payoff then combines those two, and it's a trade-off that does the person who's defining the payoff. So I say defining a payoff can be complicated, makes the person who defines the payoff decide what is important versus how important one thing is relative to another. Are there modeled with pro forma financial statements for business planning? We have some on our website with relatively simple ones, but we do not. We don't have one with a complete sort of financial planning thing. It's a good question, though. Just another question on the constrained optimization. I did understand the question. The question is, how do you constrain dependent variables to behave in certain ways? And the answer is that you need to do that within the model structure one way or another. So I say it's not always an easy thing to do, but the optimization itself does not have a mechanism for accomplishing that. So for example, you might be looking at a dependent variable and you want it to go within a certain range. And what you then do is create what's called a penalty function, which is a way of changing the payoff to decrease it if you get too close to the edge of that particular parameter. So those are some of the techniques that can be used for doing constrained optimization. Does optimization impair learning? And the answer is yes, if you used it only and did not do any manual exploration. But the really big advantage of optimization in terms of learning is you can optimize a model, see whether or not that surprises you in terms of where it is, and then look at the optimum of each of the individual parameters you're optimizing over and see how that changes behavior at the optimum. Because that is often very different from the way it changes behavior when you're away from the optimum. And if anything, then optimization becomes a mechanism for learning more about the way a model behaves. There are some simple tutorials in optimization, but to be honest, if you can run through this, it's a bit fast, obviously, but if you can run through this webinar and work with the sample models we'll be sending out, it's a great way to get up to speed just on using optimization. So is there a way to optimize flexible parameter nonlinear policy functions? So the payoff that we define in here can be any arbitrary combination of variables you want in the model. So you're in no way constrained to use anything in particular in defining a payoff. You can combine a bunch of existing elements of the model in the payoff definition, or you can write a function that does that, or a variable in the model that combines them. and you can get any kind of combination you want with any amount of nonlinearity. So optimization became available with version 1.5. The version I'm using today is 1.61, which will be out very, very soon. We've made some improvements to the performance of the optimization, but you need 1.5 or later to do optimization with Stella. This is a question about looking at the different types of variation. So sensitivity and optimization are kind of tools that can be used to work together very, very effectively. Sensitivity is usually the mechanism that's used to just discover the varieties of behavior that a model can generate. And optimization is used to kind of drive the model towards particular types of behavior we've been able to define better. They can be used hand in hand, though sensitivity is typically the more common thing to use for understanding variation. There's a question about the calibration and the integration technique. It's actually a very interesting question. And when we do the calibration webinar, hopefully I'll touch on that, although it gets a little deep. But in optimizing, in terms of the Runge-Kutta versus Euler integration, it can have a big impact on model behavior. And as a consequence, it can have a big impact on the parameter values that you achieve through calibration. They can mean different things. And so, yes, it's a very astute observation, and it is an important characteristic of calibration. So all of the models that are used in this webinar are going to be made available. You will need to have Stella Professional or Stella Architect to work through the examples that are being presented here. So I hope that answers that question. So there's another question about the differential evolution technique in terms of differentiating the different payoffs. And the answer to that is it doesn't differentiate the different payoffs. It determines the surface, the sort of most efficient surface, how you can get the most of each of them. Or let me put it another way, how you can not give up anything and keep us on one specific criteria, objective, and how you it throws away everything that is worse in a Pareto sense, where both objectives could have done better. So what it does is gives you what's called a Pareto efficient surface, or a surface that shows you the true trade-offs between the different objective functions. And that's actually a pretty important distinction, because if you just look at something that's not in an optimal state, it may look like changing one thing is going to really hurt another thing. But if you go through the differential evolution algorithm, it may show that those two actually don't have much conflict at all, that getting more of one and getting more of the other isn't that much in conflict. So it's only at the end of the optimization you can actually come to that conclusion. Okay, so I have a question about Bayesian statistics. Not surprising coming from Thomas. Okay. So you can use the optimization, this is really more into calibration than it will be into optimization, to look at the results of what's happening. And that can be a mechanism for coming up with what you believe is a better set of estimates around parameter values. Bayesian statistics is not explicitly supported, and it will not be explicitly supported in the calibration that is available in Stella. But it's certainly something that you can kind of work with on the side. That didn't really answer the question, except to say that I'm not going to answer it. So the version number 1.5 is for both Stella Architect and Stella Professional. Everything we use today was on the model window, which means it can be done in Stella Professional. Stella Architect, I did it using Stella Architect, but they behave the same in terms of the modeling interface. So there was no interface work done on these models. Which differential evolution is Kareem's specialty, and if there are other people, we've got one request for more about it, and if there are other people who are interested in it, I'm sure he would be happy to do a webinar on that. So you just need to send him an email and tell him you really want to hear about it. Okay, so I have a question about optimization only when you want to present numeric predictive results. So this is kind of a long-standing set of questions that relates to both calibration and general optimization. And in some extent, it relates to building simulation models that are quantitative at all. When you simulate a model, you get some numbers as results. And there's always the danger that people are going to look at those numbers and say, oh, that's the answer, and just think that they're done. That's never the answer. You're never done. Optimization is no different from that. It is a fantastic way to understand the sensitivity of the kinds of results you get to different assumptions you might be making in the modeling process. And it is a great way to understand the characteristics of the model that might drive you to specific values and optimization results. When you do an optimization and you get surprising results, that is very similar to doing a simulation and getting surprising results. You then have to dig back and say, why is it that changing this parameter helps when changing this parameter hurts when it seems like they do the same thing? Once you've answered that question, you've got a deeper understanding of the model you're working with and hopefully, therefore, a deeper understanding of the system you're working with. So optimization is a quantitative activity, but it can definitely lead to a lot of great qualitative insights. The great question about the fisheries model is, can you interpret the probability of crashing a fish population versus the value of what you're getting on catching? And that was a fairly simple model, obviously, but it kind of lays the framework for thinking about this. One of the problems with fisheries is we really do not know what the fish stocks are. And from what we've observed, there are different potential hypotheses about what they might be. And so going through and optimizing catch is something that has the danger of and has historically depleted fish stocks. It hasn't made them go extinct. Fish are a little bit more resilient than that particular model makes out, but it can take a long, long time for the fish population to recover. So what you'd want to do probably in a more complete fishery model is talk about the probability of going to a fast depletion of the stock in the various things and build that into some of the model framework, the model structure itself, and then use that in conjunction with the optimization. So I have an interesting question about the allocation of capital. And the question is, how can you allocate capital, basically constrained resources within a model in Stella? And the answer is that would be done using various model formulation techniques. A lot of the array functionality lets you rank and sort things and whatnot. And so you can get some trade-off there. It is also possible to do optimization over the allocations, where you'd optimize essentially over the priorities of allocating resources to different types of activities, and then have those priorities in turn be used in model equations to do the allocation between different types of activities. So optimization and the structuring of models are two things that go hand in hand. And sometimes things can end up on either side of the fence in terms of it's a part of the model structure as a part of the optimization. Many equations we write in models are themselves miniature optimizations, if you will, trying to find solutions for things. So that's a great way of, it's a great question, and it's one that has kind of an ambiguous answer, but it's you always have to think of whether or not you can do it using optimization or just using the equations themselves. Okay. So we got a question about the optimization over time, whether or not you can look at the models online. Certainly we can put all of these models up online so you can view them in the online model player if you do not have access to Stella Architect or Professional. You will not be able to do optimization in the player, but you can certainly do simulation and look at the structure of the models. Question of whether or not the Powell method is appropriate for disease progression and infectious models, the answer is absolutely yes. So when we look at any kind of model, the important thing in doing optimization is what we call the nature of the payoff surface, which is to say, when you change parameters, what happens to the thing that you've ultimately defined as the payoff. If it's a well-behaved surface in the sense of having relative smoothness and global optimum, the Powell method always works great. Even if it's got more than one optimum, the Powell method can work quite well if you're using it with multiple starts. So, and it's very effective. I've been using this, basically Powell optimization, for a long, long time, and it's helped us answer lots of really important questions. So here's the question. They've calibrated the model, and then they've run an optimization, and then the calibration has changed. And that is going to happen. And the theory behind it is you can calibrate a model because that's right, and then you run an optimization over things that you will do going forward, or that you might have done, and that will be different from the calibration. But if you're doing both optimization and calibration and they touch on the same things, you're going to get different results. The same is true of sensitivity. If you're saying, okay, I'm going to do some optimization, but you know what, I don't know about some of the behavioral assumptions, even for calibration, then that would change the nature of the calibration. So again, this isn't like a cookbook where there is one solution that comes out at the end. It's a wide variety of research techniques that can be combined. You learn a lot by building the model. You learn a lot by doing calibration, by doing optimization, by doing sensitivity. And bringing that all together is what gets us to the point where we can answer important questions about systems and their behavior. We will, as long as you join this webinar, you will be getting information about upcoming webinars. It will be a different ID for it, and Kareem is offering to do the differential evolution webinar, so I think we can look forward to that as another webinar coming up. So I'd like to thank you very much for your time. Great set of questions, and hope that we will see you at a future webinar. Thank you so much. And to get in touch with us, support@icsystems.com, or you're certainly welcome to send me an email directly, bebberline@icsystems.com.